Welcome to The Deep Dive. Today, we're diving headfirst into some really interesting research. It's grappling with a big challenge still facing large language
You mean
models.
getting them better at reasoning?
Exactly. How to make them truly better at complex, step-by-step thinking. Our source material for this deep dive is a paper from arcsignary.org. It's called Monte Carlo Tree Search Boosts Reasoning via Iterative Preference Learning. Bit of a mouthful, but interesting stuff.
Yeah, it really is.
So our goal here is to, cut through the technical jargon. We want to understand the core problem they're tackling, check out the clever approach they've come up with.
And figure out what it all means
Right.
for the future of LLMs.
Precisely. I mean, you know how impressive LLMs are getting. They write emails, code, answer questions. It's amazing.
Yeah, the progress is wild.
But maybe you've also noticed they can still kind of stumble sometimes on
Well,
things that need really careful thinking, step by step, or where getting the exact right answer is crucial.
like complex math problems or multi-stage logic.
Right. And this paper is aimed squarely at that specific capability, trying to boost that reasoning power.
That's right. LLMs have come incredibly far. But one persistent hurdle is getting them aligned, not just with human-style preferences, but with human-like reasoning processes.
So we want them to think more like us in a structured way.
Yeah, exactly. And you need data for that, specifically preference data showing the model good versus bad examples.
But the paper argues there are issues with how we usually use that data, right?
Totally. A lot of current methods, they use these static reward models, or they train offline with RLHF reinforcement learning from human feedback.
And the problem there is,
Well, the feedback loop isn't live. It's not dynamic. The model isn't really adapting continuously as it goes. It's trained on a fixed data set of preferences.
okay. And the feedback itself, the paper mentioned it's not very detailed. They called it sparse supervision.
Yes, exactly. Think of it like grading an essay.
Hmm.
Often, preference data is just instance level, meaning you just get the whole essay, the whole final response, a thumbs up or thumbs down.
Right.
And you lose all that valuable info about why it was good or bad, like which specific steps in the reasoning were right or wrong. You're only judging the end result.
Okay, so they needed something more dynamic, something that gives feedback on the thinking process, not just the final answer. And that's where their solution comes in. MCTS Enhanced Iterative Preference Learning.
That's the core idea. They've built this iterative approach. It's kind of inspired by systems like AlphaZero. You know, how it mastered games by constantly refining its strategy through self-play and search.
Okay, so continuous improvement. And central to this loop is Monte Carlo Tree Search, MCTS.
Right, MCTS.
Yeah.
That technique, famous from Go programs, other game AI.
Mm-hmm.
But here they're applying it to language reasoning.
How does it work here? Like a coach?
Sort of, yeah. It acts like a policy improvement operator. It helps the LLM transform its current reasoning strategy, its current policy, into a better one.
And instead of just that thumbs up, thumbs down on the final answer.
They use MCTS to get feedback on the individual steps the model takes.
Step-by-step feedback.
Precisely.
Mm.
MCTS has this look-ahead ability, right? It explores different possible paths. They use that to break down the feedback into these step-level signals.
Okay.
Plus, they add another layer, stepwise self-evaluation. The model actually assesses its own intermediate steps.
So it checks its own work as it goes.
Kind of, yeah. It helps improve consistency, like, does this step feel right to me?
Okay, so you've got MCTS exploring steps, the model evaluating its own steps. Then what? How does the model learn from this?
They use this incredibly detailed step-by-step feedback to update the model using direct preference optimization, or DPO.
DPO, why DPO?
Well, the paper suggests it's a more stable way to use this kind of preference data compared to, say, traditional reward modeling in RLHF.
Gotcha. And the crucial part you mentioned, it's an online loop.
Yes, this is key. It's not offline training. The model uses its current strategy. MCTS explores and finds better step-by-step paths. Based on that strategy, it collects that granular feedback. DPO updates the strategy.
And then it immediately uses that new strategy for the next round.
Exactly. It's a continuous self-improving engine, laser-focused on the reasoning process itself.
Okay, this is where it gets really interesting for me. How does MCTS, a game-playing algorithm, actually plug into an LLM's thinking process?
Right, let's unpack that. So imagine the reasoning process, generating an answer step by step as a sequence of discrete actions, like generating the next chunk of text, the next token sequence.
Okay, each step moves you forward in solving the problem.
Yep. Each step transitions the state. Now, MCTS, using the LLM's current policy, its current best guess for how to reason.
It samples different possible next steps.
Exactly. It generates candidate steps. But it doesn't just pick one randomly. It uses its look-ahead capability. It simulates, okay, if I take this step, what might happen next, and the step after that.
So it's trying to predict which paths are more promising down the line.
Yes. It estimates how good different sequences of steps are likely to be. And that estimate isn't just about the final answer.
What else goes into it?
It's refined by combining two things. One, the model's own self-evaluation score for that specific step, how confident it feels about it.
Okay.
And two, whether the paths explored from that step actually ended up leading to the correct final outcome, if we know it.
Ah, so the reward for taking a certain step is a mix of the model's internal confidence and the external reality check. Did it work?
You got it. It's a clever blend. So MCTS builds this search tree by exploring lots of these different step sequences. It uses principles from game AI, like balancing exploration, trying new things, with exploitation focusing on paths that already look good. Uses things like Q values and visit counts, like the PUCT formula they mentioned.
Standard MCTS stuff, basically.
Pretty much.
Yeah.
Selection, expansion, back up the usual MCTS cycle.
Okay, so it builds this tree. How does that tree give them the step-level preference data they need for DPO?
Right, so after the search is done for a particular problem, MCTS has assigned values, these Q values, to lots of different potential steps at different points in the reasoning chain.
These values represent how good MCTS thinks that step is.
Exactly, the estimated future values starting from that step. And they use these Q values to label preferences. If step A consistently led to higher estimated values in the search compared to step B at the same decision point,
Then A is preferred over B.
bingo. The search process itself generates the detailed training data. Pairs of steps, one preferred, one dispreferred, based on the MCTS exploration.
That's really neat, using the search not just to find a good answer, but to generate the training signal itself.
Yeah, it's a core part of the innovation here.
So once they have this valuable step-level preference data generated by MCTS,
They feed it into DPO to update the model's policy.
right, and DPO adjusts the model so it's more likely to take the preferred steps next time.
Precisely. It directly optimizes the policy based on those preference pairs, making it less likely to choose the dispreferred steps, more likely to choose the preferred ones.
They mentioned something about a conservative version of DPO and adaptive label smoothing. What's that about?
The conservative DPO is just a slight tweak to the standard DPO loss, potentially for stability. The adaptive label smoothing is interesting, though.
How so?
Well, since the preference labels, A is better than B, come from those estimated Q values in MCTS, there can be some noise, right? Especially if MCTS didn't explore a particular branch very deeply.
Sure, the estimate might not be super reliable.
Exactly. So adaptive label smoothing basically says, let's soften that A is definitely better than B label a bit based on how much we actually explored A and B. If the visit counts were low, maybe we're less certain about the preference.
Okay. It accounts for the uncertainty in the MCTS-derived labels, makes the training more robust.
Yeah, that's the idea. And again, just to hammer it home, this updated policy from DPO
Is what gets used in the next round of MCTS exploration.
absolutely crucial. It's learning from its newest self, creating that powerful online self-improvement loop. It's not learning from old data generated by a weaker version of itself.
Yeah, the paper really emphasizes that online aspect. They even provide some theoretical arguments for why it matters so much.
They do, and it's quite insightful. They contrast it with traditional offline methods, where you might generate a big data set of preferences once, using a fixed model, and then train on that.
And they argue that can fail.
Yeah, Theorem 3.1 highlights this. Think about it. If the fixed older model you use to generate data never happened to explore certain stupid mistakes that your current model might make.
Then there's no data to teach the current model not to make those mistakes.
Exactly. You can't learn to avoid errors you never see examples of. The offline data set might simply lack coverage of the weaknesses of the policy you're currently trying to improve.
Okay, that makes sense. But the online setting avoids this.
That's the argument in Theorem 3.2. Because the sampling policy is the current policy, the model is constantly exploring the kinds of reasoning paths it is currently prone to taking, including the suboptimal ones.
So it's more likely to encounter its own flaws and generate the data needed to correct them?
Precisely. Sampling from your own evolving policy makes it much more likely you'll eventually learn to avoid your own specific failure modes. The theory suggests this online approach is much better at converging towards an optimal policy.
Interesting. So the theory backs up the intuition that learning from your current self is better.
Yeah, it provides a more formal grounding for why this online iterative process should work better than static offline training.
Okay, theory is compelling, but the big question, did it actually work in practice? They tested it,
Oh
right?
yeah, they put it through its paces, evaluated it on arithmetic tasks, GSMAK, and math. Those are standard benchmarks for multi-step math word problems.
Which are notoriously hard for LLMs.
Very much so. And also on a suite of common sense reasoning tasks, things like ARC Challenge, AI2SciM, OBQA, CSQA, plus an unseen dataset, SciQ, to check generalization.
And the base model they used was mostly Mistral 7B.
Mostly, yes. They did some checks on Llama 213b2 just to show it wasn't specific to one architecture. They compared their MCTS iterative method against standard supervised fine-tuning SFT and also against offline versions or instance-level versions of their iterative approach.
And the results, were the improvements significant?
Yes, quite significant, especially compared to just the SFT baseline. On arithmetic, GSMAK accuracy jumped from about 76% to nearly 82%.
Wow, that's almost a 6% absolute improvement. That's substantial for GSMAK.
It really is. And on math, which is even harder, it went from roughly 29% to almost 35%. Again, nearly a 6-point gain.
Okay, so definite wins on math reasoning. What about the common sense tasks?
Some really dramatic gains there, too. On ARC Challenge, accuracy leaped from around 60% to over 76%.
Whoa, a 15-point jump. That's huge.
Huge gain, yeah. And on SciQ, the unseen data set, performance went from about 81% to over 88%. Another solid gain of over 7 points, showing good generalization.
That's impressive. But you mentioned earlier, maybe not all tasks saw such big gains.
Right. They noted more modest improvements on OBQA and CSQA compared to some other tuning methods.
Any idea why?
The paper speculates it might be related to the base model's underlying knowledge. On tasks needing very specific facts, encouraging longer reasoning chains, which this method tends to do, could potentially lead the model to hallucinate or introduce errors if it doesn't actually know the facts required for that chain.
Ah, so there's maybe a trade-off. The push for longer, more explicit reasoning works great when the model can reason correctly, but might backfire if it lacks the core knowledge for that specific problem.
That seems to be the interpretation. It highlights that reasoning skill and factual knowledge are intertwined. You need both.
Okay, so the headline results are strong, but with some nuance. Did they dig deeper into why it works? Any ablation studies?
They did. Several interesting analyses. First, they confirmed that the step-level feedback really is generally better than just instance-level feedback,
So focusing on the process pays off.
especially on those common-sense tasks like ARCC and SciQ, where the step-by-step logic is arguably more central than in, say, a single math calculation.
Makes sense. What about online versus offline? Did the analysis back up the theory?
Mostly, yes. The online iterative learning generally outperformed its offline counterpart, again, particularly on the common-sense tasks, showing that adapting to your own evolving policy is beneficial.
But sense of but.
Well, interestingly, on the really hard math dataset, if they didn't incorporate ground truth answers during MCTS, the online versus offline difference wasn't as stark, especially if the starting SFT model was already quite strong.
Huh. So maybe if your starting point is good enough, offline can still get you quite far on some tasks.
Potentially. It suggests online is perhaps more robust or helps more when the initial policy isn't great, but the gap might narrow on certain tasks if you start strong.
You mentioned ground truth. How much did that help, allowing MCTS to see the right answer sometimes?
Oh, massively. When they incorporated ground truth solutions into the MCPS data collection, basically letting the search know what a correct path looks like, it significantly improved the accuracy of the preference labels generated.
Better training data, basically.
Exactly. And that led to much bigger performance boosts, especially on the really challenging math dataset. Having that perfect example helps guide the search and the learning much more effectively.
Okay. And the self-evaluation part, where the model assesses its own steps. Was that useful?
It was. They found it provided consistent improvement on top of just using the outcome correctness. And importantly, they found the self-evaluation scores were much more reliable and discriminative when the prompt included an example of a correct answer, like the ground truth.
So giving the model a reference point helps it evaluate itself better.
Seems so. It anchors the self-assessment.
What about computational cost? This sounds more complex than standard fine-tuning.
It definitely involves more compute during the training generation phase because of the MCTS search. But they did an analysis showing it has a better compute scaling exponent, meaning
more training compute gives you proportionally better results. It uses the compute effectively.
yeah, especially on the unseen SciQ dataset. suggesting it's efficient in leveraging compute for generalization. They also noted that just using MCTS at inference time, sampling only, can boost performance, but this iterative learning pushed results even higher on ARCC and PsyQ, though interestingly sampling only was slightly better on math in their tests.
Okay. Any other interesting tidbits from the analysis?
They did observe some performance fluctuations during the online training iterations, kind of like cycles, which aligns with their theory that you need to optimize sufficiently in each DPO step to avoid instability.
Right. And qualitatively, did they look at how the reasoning changed?
Yes, they had examples.
Yeah.
On math problems, the step-level guidance clearly helped the model build longer, correct reasoning chains where the baseline failed.
That's the goal.
But, echoing the earlier point, on common sense tasks like OBQA, sometimes the longer chains prompted by the method introduced errors or strayed into hallucinations, reinforcing that balance needed between encouraging thoroughness and maintaining factual accuracy.
Fascinating. So it's powerful, but needs careful application depending on the task.
Seems that way. They also show that things like MCTS search breadth matter, and that the outcome correctness signal is dominant, but self-evaluation adds value. And crucially, the approach worked with other preference loss functions besides DPO and on Llama 213b, suggesting it's a generally applicable technique.
Okay, so pulling this all together, how does this research fit into the bigger picture of what's happening with LLMs?
Well, it sits right at the crossroads of several really active research areas. You've got iterated learning inspired by AlphaZero, related to things like STAR or self-rewarding models.
Where the model keeps refining itself.
Exactly. Then there's self-training, using model-generated data, preference learning like RLHF and DPO, and also guided search methods for reasoning like chain of thought, tree of thoughts, process supervision.
Lots of related ideas trying to make reasoning better.
For sure. We've seen systems that iterate or use self-generated data or use preferences or use search.
So what's the key differentiator here?
I think it's really the novel combination. Specifically using MCTS for step-level feedback, integrated into an iterative online preference learning loop with DPO. It's that specific recipe using powerful search to generate granular, process-focused training signals dynamically that seems unique.
Got it. So what's the main takeaway for you listening to this?
Well, this research presents a really compelling and seemingly effective new way to train LLMs for better reasoning. By combining the search power of MCTS with iterative preference learning, and crucially, focusing on the intermediate steps of the thinking process, they've shown some pretty significant improvements on tough reasoning tasks, using MCTS not just for inference, but to generate detailed step-by-step feedback, and then using that in an online loop with DPO to refine the model's policy seems quite powerful.
Yeah, it really highlights the value of looking beyond just the final answer, right? Focusing on the process of getting there seems key.
Absolutely. It underscores this growing realization that improving LLMs isn't just about scale or more data, although that helps. It's also critically about improving the actual mechanisms they use to reason and solve problems, teaching them how to think.
Which leaves us with a really interesting question to chew on, doesn't it?
Mm-hmm.
As these models get applied to more and more complex challenges, how much of their future improvement is going to come from just making them bigger, more parameters, more data, and how much will come from sophisticated training techniques like this one, techniques that explicitly teach them how to break down problems and reason through them more effectively, step by careful step?
That's a great question. The balance between raw capacity and refined technique.
Something to mull over as we watch these incredible models continue to evolve.